Yo! Hope you had a blast participating in the flame test lab yesterday. Be sure to get out your spiral to continue your notes from yesterday. The page again is 55. Let's quickly review what we saw yesterday. Visible light can be described as having a long wavelength, like the color red, or having a short wavelength, like the color violet. We can also relate wavelength to energy. So we can describe a long wavelength as having low energy. And we can describe short wavelength as having high energy. There is a third term in which we can describe a wave. This is frequency, symbolized by the letter F. Frequency is how often waves pass a given point per second. The SI unit is hertz or inverse seconds. They are practically the same. And so we can see low frequency as those wavelengths being farther away from each other by the picture located on the top. And then the shorter wavelength, the wavelengths are much closer to each other, and that could be described as high frequency.
So today, Mr. Neutron is going to demonstrate the slinky, representing wavelength, frequency, and energy. So first off, we're going to be creating a long wavelength. So notice the wavelength is long. Mr. Tran is not using much energy to create this long wavelength. Okay, the frequency is also low. Now we're going to try creating a shorter wavelength. So notice that the wavelength is very, very small and the frequency is high, and I'm using a lot of energy right now to generate these small wavelengths, y'all. A lot of energy, a lot of energy.
Hopefully y'all now know the relationship between wavelength, frequency, and energy. So let's summarize it here. Long wavelength is equal to a low frequency, and that is also related to low energy. Remember, it didn't take a lot of effort to make that long wavelength. But for a short wavelength, it is high frequency, and it required a lot of energy to generate. So high energy. Let's relate wavelength and frequency. We have this equation, C equals wavelength times frequency. C is a constant, meaning it will never change. C will always be equal to 3 times 10 to the 8 meters per second. Next, we have this upside down Y looking thing, and this is the Greek letter lambda. I draw it as a curve and then a straight line. The unit for wavelength is meters. F represents frequency, and the unit is either hertz or the inverse second. And so these two are the same thing. You can just think of them as either or and use them interchangeably. Problem solving in chemistry is always going to be the same. Let's read the problem. What is the frequency of red light with a wavelength of 6.90 times 10 to the negative 7 meters? So we are solving for frequency, so I'm going to be boxing that, knowing that we don't have a value for frequency and that we are looking for it. The first step is always to list off my givens. So what's given in the problem? So I always list the givens in the order of the equation I'm using. So this is frequency and wavelength. So it's C equals wavelength times frequency. So let's start with C. C is always going to be 3 times 10 to the 8 meters per second. Remember, that doesn't change. It's a constant. Next, I have a wavelength that's given to me in the problem. And finally, frequency, which is what we are solving for, so it gets a question mark. Next, I like to write out the equation. C equals wavelength times frequency. The next step is that I need to isolate my variable that I'm looking for. So that is F. So in order to do that, I need to divide both sides by wavelength. And when I do, wavelength cancels out, and I get frequency equals C divided by wavelength. Once I have that variable isolated, I'm going to plug in the numbers. So C was 3 times 10 to the 8, and wavelength was 6.90 times 10 to the negative 7. Meters cancel out, so I'm in the inverse second as my unit. I divide the two numbers and I get this value here. But you might be asking, Mr. Tran, how do I know how to round? So you always round to the fewest sig fig because all we're doing is dividing. You will never use constants when deciding how to round, so we will never count constants, y'all. Our constant is that 3.00 times 10 to the 8. We're not going to take that into consideration. So the only number that I'm going to be counting is the given number, which is 6.90 times 10 to the negative 7. And remember, when we have scientific notation, I just like to ignore the times 10 when counting the sig figs and count this. So we have 3 sig figs. That is why the answer is 4.35 times 10 to the 14th inverse seconds. Next, we're going to relate energy and frequency. So the equation is E equals H times F. So E is energy, and the unit for energy is joules. H is another constant. It's Planck's constant. And that number is 6.63 times 10 to the negative 34 joules times seconds. And finally, we have frequency, which is F, and that again is in hertz or inverse seconds. Let's calculate another problem. How much energy does a photon of light with a frequency of 4.60 times 10 to the 14th inverse seconds have? In this problem, it looks like we're going to be looking for energy, so I'm boxing that because that's a variable we are looking for. Next up, I'm going to be listing my variables in the order of the formula or equation. It's E equals H times F. So E is a question mark. We don't have it. H is a constant, y'all. It's 6.63 times 10 to the negative 34 joules times seconds. And finally, we have frequency, which is given to us as 4.60 times 10 to the 14th inverse seconds. Next up, I'm going to list out the equation. E equals H times F. Looky here, y'all. Energy is already isolated, so I don't need to rearrange my equation to isolate the variable I'm looking for. E is by itself. So now I plug in my numbers. H is 6.63 times 10 to the negative 34 joules seconds. And then F is 4.60 times 10 to the 14th inverse seconds. So these seconds and inverse seconds cancel out. And then I multiply to get 3.05 times 10 to the negative 19. And again, the reason why it's only 3 sig figs in my final answer is because I count the given number. We never ever use the constants to round. Okay, so I'm counting my number here. There's only 3 sig figs, so I round my answer to 3 sig figs. Chemists study electromagnetic radiation to get information about an atom structure. With electrons being on the outside of the nucleus within an atom, electrons are these subatomic particles that are responsible for absorbing energy. And when they absorb that energy, they also lose that energy because they can't hold on to it. And when they do lose that energy, light is emitted. So we can see that in our diagram here, the electrons being on the outside, it absorbs energy and goes into a different arrangement. But the electron can't hold on to that energy. So when it releases that energy, it goes back down to its position. Okay, so this energy is represented as the light, and in this case is purple. And when we see purple light, we know purple light has a short wavelength, and a short wavelength represents high energy. Okay, so the light can either be described as high or low energy based on our knowledge about the relationship between wavelength and energy. Different elements, y'all, have different electron arrangements, and we'll see this on Monday, so the light produced when heated would be different. And that's all for today, y'all. Have a good one.